Making history. All right, so you'll be on here for forever, at least for the next 6 years. Wrong page. Okay. All right, so yesterday, they used to do parametrics in Math 3. They were saying that's not something that looked familiar what we did yesterday, which is fine. We usually spend the day kind of reviewing all of that, and then now today is like the calculus stuff of this, okay? So first thing is actually an old idea. We can combine kind of with this new topic. It's an old idea. If I wanted you to find the slope of a curve, all right, so if we are taking the derivative, if we're looking for the slope, all year we've talked about our slope is just, instead of delta y over delta x, it is now dy over dx, okay? And we've talked about this in the past, that if I now took this equation here, so if I took the derivative of x in terms of t, that should give me dx dt, right? This is x in terms of t. If I took, and that's not our answer, because what we are trying to find is dy dx, all right? Change in y over change in x on the xy plane. If I took the derivative of the y equation, that would be dy dt, and then that would equal whatever the right-hand side would equal. If I am looking to create this ratio here, the dy over the dx, can't we accomplish that by just taking the dy dt equation, dividing it by the dx dt equation, the dt's cancel, and we end up with that ratio that we're looking for. Okay? Kind of an old idea we talked about a long time ago, first few days of the chain rule. All right, but it applies to these as well. So, a couple problems here, because this is not particularly hard. So go to number 1. If I am asking you to find dy dx, so that's the set of directions for numbers 1 and 2. If I took the derivative of this first equation, x equals t squared, we would write this as dx dt would equal 2t. But again, that's not the ratio that we're trying to find. All right, well, take the derivative of the y. These guys are very popular today. Okay, she's taking a test right now, though. Okay. If we found the derivative of the second one, this is y in terms of t. So we would say dy dt, and then just take the derivative of the right side, 4t cubed. And then again, if we are trying to find dy dx, we can create that ratio by doing what we said we can do up here. Take the dy dt expression, which is 4t cubed, divide it by the dx dt, which is 2t. This one will reduce a little bit, down to 2t squared. And then what we've talked about all year, we would like to find our vertical change as it relates to the horizontal change on the xy plane. So we would like this variable to be x, if at all possible. We've definitely dealt some where we can't. But in this instance, we can, because what is t squared equivalent to earlier up here? X. All right, right here we see that t squared is equivalent to x, so we can go ahead and rewrite this as 2 times x, and then that would be our answer. All right. 2, largely the same. If we did the derivative of the x, that's x in terms of t, so we would write that as dx dt. And then that's just secant tangents. The derivative of y is y in terms of t, so we'd write that as dy dt. And then that would give us secant squared of t. And then now for the third time here, that dy dx that we are looking for should be the dy dt, so this guy here, secant squared, divided by the dx dt, which is that secant t tangent of t. This one also I would suggest simplifying it if you can. The secants would reduce, so you would end up with secant of t over tangent t. That actually reduces more, but because we have a time to plug in, it's pretty straightforward right now if we just plug it in now. All right, denominator is the easy one. What is the tangent of pi over 4? 1. So our denominator is a 1. And then the secant is the reciprocal of cosine. What is the cosine of pi over 4? root 2 over 2, and we want the reciprocal of that. So that would be 2 over root 2 divided by 1. And then, obviously, divided by 1, you just get 2 over root 2. Rationalize that. I'm running out of screen up there. Let me do it down here. 2 root 2 over 2 then should just simplify to be root 2. All right. All right, so that's how we can find the slope. All right, 3. This was a little unfortunate on the test because most of you had this question. Write the equation of a line tangent. It's probably the most common question we've done all year. It's been a minute since we've had to do one before Friday. What 2 things did we always say we need to write the equation of a line? Yeah, point and a slope, right? So we need to find our point, and you need to find your slope. Let's do the point first. X, Y, here's how you're going to get X. So X in this problem should be 2 times the cosine of whatever time we're evaluating it at. And in this case, we are evaluating it at the pi over 4. So X should equal 2 times the square root of 2 over 2. So when those cancel, we now know that our X coordinate is root 2 over 2. You're going to do the same thing with the Y. Oh yeah, multiple. Oh yeah, good call. And I have that right there. Yeah, just root 2. Thank you. Okay, you'll do the same thing with the Y. You'll get 2 sine of pi over 4. That's also root 2 over 2 times 2. So the exact same thing happens. That should give you a root 2 as well. And then our slope is what we just did up here in number 1 and number 2. We need to do dy dt divided by dx dt. Whatever that evaluates to be ends up being the slope at that point. So dy dx, again, is the dy dt, whatever that ends up being, divided by your dx dt. So take the derivative of your y. So here is again the y. So you'll get 2 cosine of t. The bottom is the derivative of x. Here is the x equation. So that should be a negative 2 sine of t. And then you're going to evaluate that at pi over 4. Okay. All right. 2 divided by negative 2 is a negative 1. And then different ways you can kind of process this. You could evaluate each of them. You can treat it as a cotangent of pi over 4. However you do it, when I do cosine of pi over 4 divided by sine of pi over 4, what's that going to give you? Yeah, just a 1. So overall, then, our slope is a negative 1. I shouldn't box that because that's not our final answer. And then when you write the equation of a line, once you have these 2 things, we just write our line. So y minus root 2 equals a negative 1 times x minus root 2. All right, and then that's our line tangent. Okay, good with that. Okay, we'll do one more of these. We don't need to do 4 of them. So we'll do 4, and then we'll go to the back. Same process, though. We're going to write the equation for your line tangent. Always means you need a point and the slope at that point, which is, again, the dy dx. Oh, you can't see that on yours, can you? Okay, so the point, super easy in this one. X equals t. So if your t is 1/4, that means x is 1/4. Y is the square root of your time. So the square root of 1/4 is 1/2. And again, your slope is the dy dx. So this is the one that requires a little bit of work. And dy dx is the dy dt over the dx dt. So we want those derivatives. So dy dt, just be careful, understand, just for whatever reason, fraction powers cause issues. So this is a t to the half. So when we take dy dt, it should be 1 half t to the negative half. The derivative of x is just x equals t, so that's just going to give you a 1. I'd clean that up first. So this is really 1 over 2, so 1 half, and then a root t in the denominator. Evaluate that at the time of 1/4. And then again, square root of 1/4 we did earlier, that's a half. So overall, that slope should just be a 1. And again, once we have our point and our slope, then we go ahead and write the equation. So y minus 1 half equals 1 times x minus 1/4. Okay? Okay. Then 5 and 6, we don't need to do those. It's the same stuff. I think you get the hang of this. We find the slope, get your point, and then write that equation. All right, now, back page. These you need your calculator, so go ahead and pull those out. The quiz that you're going to take next week on this, part of it's without your calculator, part of it is with. Everything on the back page here would be with your calculator. All right, so number 7 says a particle moves in the xy plane so that its position at any time, so grant me that we're going to have a negative time here, just go with it, is given by, and then you're given, this is your x position at any time, and then this is your y position at any time. All right? All right, all I want you to do in part A, to make sure we know how to graph it, in parametric, change your window, all the stuff we did yesterday, is to sketch here what that graph would look like. Okay? So this is our T max, T min. When we're in parametric, this is what you're going to graph for the x function. This is going to be your y function. Okay? So sketch that. And then when you sketch it, it should kind of look like an integral sign, actually. Not intentionally, it just happened that way. Let's see. Okay, so when you graph it, again, should look like a little integral sign. It does go through the origin. It kind of looks like this. Okay, we all got that? Then, I also wanted you to indicate the direction of motion. So when I ask you to do that with a calculator question, I probably should have prompted you to read that and do that right when you graphed it, because you got to look at it really carefully, and then as it's getting graphed, the direction that it's graphed is the direction of motion. So when that thing graphed, did it go from left to right or right to left? Yeah, it went right to left. So put some arrows here indicating that this was the direction that that thing moved. All right. So it started here, and then it went right to left, and then finished down there. Yeah. What's that? There's no arrows on the what? Oh, right, because it starts and stops there. Yeah. Okay, part B. And then now we're going to tie some old stuff together, some old calculus ideas with just a parametric equation. So it now asks, on this time interval, so the time interval that we just graphed it, when does x of t achieve its maximum value? So old ideas, we haven't talked about this a ton recently, the chapter 7 test we did with maximizing the number of people in the park, when was there a max, all of that. But if we are going to try and maximize x of t, this is our whole little candidates idea. What for sure are 2 potential places where we could have our maximum x position? At the end point. So -1 and the pi. Then, if we are maximizing x of t, then the way we find maxes is when our derivative, but since I'm just trying to maximize our x position, It would be when our derivative of x is either 0 or undefined. So while there's a y equation up there, because we're only trying to figure out what our maximum x position was, we're only going to work right now with this equation here. So we want to take the derivative of x. So it's a natural log, so you would do 1 over the inside times the derivative of the inside, and then minus the derivative of that t, which is a 1. All right, as we set that equal to 0 and clean it up, first question, is there any place where your derivative would be undefined right now? Is there a time where this is undefined? Yeah, a -2. All right, is -2 in our window, though? No. So because it doesn't fit here, we're not going to worry about that -2. But we can also now set that equal to 0 and solve this. So if we now try and solve this, add your 1 over, go through those steps, multiply the t plus 2 over. We do get another time, but isn't that already identified over here as our endpoint candidate? Okay, so we don't get anything extra. All right, so what we would then do when we were doing these, let's set up our sign chart, starting at a -1 to pi. And again, -1 satisfies both the idea that it's an endpoint. Oh, that's actually intentional. It's Neil's time. All right, Neil, I'll give you 1 more minute. All right. And you need to log off, or I'll kick you off here. Okay. So pick a good number. Again, don't be too creative here. The number between here that we want to use is 0. Go to your derivative. So again, here is our simplified derivative. If I let my time be 0, so if I plug in a 0 right here, won't I get 1/2 minus 1? 1/2 minus 1 is negative. So what that means is, and I'll relate this to our graph. If our graph started here and it went backwards the whole time, wasn't our x position decreasing the entire time if we were going left? Isn't that what this is also now confirming and telling us that happened? So the answer to the question then is, when do we have, what time were we furthest to the right? Wasn't it right at the beginning, at the time of -1? Okay? So in terms of that initial answer, you're going to say at the time of -1. That's one of our answers. And then the second part now is, once we've established that, what was the position at that particular time? So now we're going to go back up. Let me make this a little smaller. Here is your x position. Here is your y position. We now need to find x of -1 and y of -1. And then whatever those decimals are, that's why we're going to use a calculator, whatever those values are, that is your position at that particular time. Okay? So plug in that first one, and then again, we can compare it to our graph. Get your x value, because this one we could actually do without a calculator, but go ahead and use your calculator, because that's probably what we would do if we had it in our hands. What x position do we get at a -1? Yeah, it's a 1. Should be +1. Look at your graph now. If I go up to my graph, you can look at your graph again if you hit graph, and you would see that's when we started. At 1, that was your maximum x position, and then we worked left the rest of the way. Okay, yeah. You could. Yeah, yes.
So t is equal to -1, and I plug -1 t for the x.
For this one?
Yeah.
Did you get the minus t in the back end too? Yeah, and then that's a plus the 1. Okay? All right, and then throw in -1 for your y. What's that give us? And we should get, let me leave a little room to operate, 2.524. That's a 4. Okay, good with all that? Okay, we'll get the next one started. Number 8, this is an old free response question that fits nicely, kind of first day, to kind of understand what all these different things ask. All right, It's all calculator, but kind of word for word, one of these old questions. And I kind of like it because, again, it outlines kind of everything that we're talking about with this. So it says the position of a car, of a roller coaster car, can be modeled parametrically by, and then you're given your x position and then your y position. X and y are measured in meters, and the time interval that you were given is 0 to 18. The derivative of those functions, so they were really, really nice this year because they actually took the derivatives for them so that they couldn't mess this up. All right, so they have the derivatives for you. All right, and like I said, the A's tend to be really nice. As long as we can get the A's, that's 2 or 3 points. Largely ensures you get at least a 3 on the AP test. So do part A, and you should hopefully find that again really nice. It should be about the 5th or 6th time today we've done it. And again, don't just give the answer. I know you have your calculator. This is, my guess is probably 2 points, and the answer point is just one of them. So you want to show what you're actually plugging in. So show that on the paper and then use the calculator to get the value. But don't just put the numerical answer. And by showing it, you don't necessarily have to show that the notation. You don't have to show the dy dt over the dx dt. But you definitely want to show that you are taking these functions and you're evaluating them at the 1. So you could, you can abbreviate it. So you can do y primed of 2 over x primed of 2. That's fair. It saves you a little bit of time versus writing all those ugly functions out. But that's our slope. dy dx is dy dt over dx dt, so y primed over x primed. And that should give you 1.794. Okay. On your way to your 5, I'm here. All right. Okay, good with that. All right, letter B. Let's get letter B done. And again, this is kind of why I like this question and why I liked it when they took it this year. When it says find the vertical position, you now have 4 different equations. You have this equation, we'll call that 1, 2, and then these are 3 and 4. Of those 4 different equations, which one is the vertical position? 1, 2, 3, or 4? 2. Y of t is your vertical position. So when this asks you to find your vertical position, you're going to be using this guy here. We're ultimately looking for how far up are we at a particular time. It would be easy if it just said find the vertical position of the car at the time of 4, because then you would just plug 4 into this. All right, not that easy. They want you to find the vertical position when the horizontal position of the car, which is which of these 4 up here? 1. When the horizontal position of the car is 140. So if equation number 1 is your horizontal position, which it is, this really translates to you taking x of t, the horizontal position, and setting it equal to 140. That's going to give us the time that we are going to use to find the vertical position at. So we got to figure out what is the time when our horizontal position is 140. All right? And this, again, very much calculator. You cannot do this without your calculator, because as you now set x of t, so this guy here, the 10t, plus 4 sine of t equal to 140. This is one of the ones you can't do by hand. You have your 2 options. You can do the intersection, graph them separately, see where they intersect. The safe way is to set it equal to 0 and then graph one equation. Uh-oh, too big here. And then find the 0. And as long as you can see the x-axis, this is why this is the safer one, you should be crossing the x-axis somewhere, because that somewhere is the time you're going to plug in over here. All right, see if you remember how to do that, because it has, I don't know if we've done one of these this whole semester. Oh yeah, good call. So now that we are only using one variable, or one equation with one variable. You don't want to be in parametric anymore. So you're now going to have to go back to function notation. So go to your mode, move back into function. Yeah, thank you, sir. And then you're going to graph this and then see if you remember how to find the zero and that whole process. And there's a little trick to this too. See if we get this. Okay, then about half of first period just sat there quietly and didn't say anything. And were confused, and they didn't say anything because they didn't see the graph at all, but they just sat there. Are we finding our graph? Okay. If you don't find your graph, it is because what does our window need to be? Yeah, what should, just set it to what? To make your life the easiest. 0 to 18. Okay? And then that way you're only looking at the window you're concerned about. So you can go to your x min, make it 0, make your x max 18. And then now if you don't see it across the x-axis, then something's wrong. Okay, let me not circle that so we think that's our answer. And then you'll see it's a little bit bigger than 10, so that's why you wouldn't have been able to see it. And then you are going to take this number and you're going to use that in a calculation. So write every single decimal you can. So this should be, what was the time? 13. Yeah, and then write them all down. So our time should be 13 point. Yeah, I'm going to run out of space here, but put all those decimals in here. Because now you're going to take that and plug that in to the vertical position equation, which is ultimately then the answer. Okay? All right, and when you do that, what do we get? Should get 3.363. Okay? Okay, so get that. If you don't, let me know. This is a good stopping point. And then we'll do C, D tomorrow. All right, we'll do that at the beginning. We have some time to play with tomorrow. I'll give you back the paper part of your test. I'll open up the online part so you can kind of see which of any of those you missed. Don't freak out too much. I was a little surprised. I thought the test would be a little better. I don't know if it's the online thing, and that was what I was kind of worried about with the AP test, which is why I did this. So kind of let me worry about the grades. I did make one of these for you, so if you were not happy with that test and you want an opportunity to get some of those test points back, I made one of them for this chapter. Okay? Again, if you want to piecemeal it, you can do the first one or two. All right, we've done the derivative of parametric curves. We've done tangent lines of parametric curves. If you want to wait till the end as a big test review, feel free. But this is one I'll give you some extra credits for this. And this test is nice. This is the easiest test of the semester. Now that it's easy, don't fool yourself. But of the four that you're going to take, this is the nice one. Okay? But do what you want with that.